Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. We're going to go over the first free response from the energy unit. Hopefully you guys are excited about energy. Hopefully you feel confident about this unit. Let's take a look at this first problem. So we got this roller coaster ride. By the way, it was very funny looking at your responses and seeing you guys try to draw this roller coaster track. I get some really weird shapes for this little loop right here at where it says B. But anyway, a roller coaster ride in an amusement park lifts a car of mass 700 kilograms to a point A at a height of 90 meters above the lowest point on the track. As shown below, the car starts from rest at point A, rolls with negligible friction down the incline, and follows the track around a loop, radius 20. Point B, the highest point of the loop, is 50 meters above the lowest point on the track. Indicate on the figure the point P at which the maximum speed of the car is attained. Okay? So that would occur, so at the top here we have potential energy, gravitational potential energy, right? And since we're not moving, we have no kinetic energy. Now, as that cart goes down the ramp, right, all of that energy becomes kinetic energy. Okay. We are assuming Earth is part of the system, therefore no work is being done. Therefore, the initial energy, the potential energy, should equal the final energy, the kinetic energy. Okay. Calculate the value of this maximum speed. Okay. So we know in the beginning, initially, needs to equal the final. Right? That, and again, that's because we're including Earth as part of the system, so no work is being done. Remember that? Okay, so the initial energy equals the final energy. Initially, we have gravitational potential energy, and in the end we have only kinetic energy. Okay. What's the equation for gravitational potential energy? It is mgh. That is on your equation sheet. And what is the equation for kinetic energy? It's 1/2 mv squared. That is also on your equation sheet. We have gone through these equations so many times that you shouldn't even have to look at the equation sheet to find these. They should be almost automatic. Potential energy mgh, kinetic energy 1/2 mv squared. Okay. Notice that there's mass on both sides of the equation, so we can cancel out the mass. We're going to rearrange for velocity because that's what they're asking for. So this means this is 2gh equals v, and this is square root. Okay, that means this is the square root of 2 times 9.8, or you can use 10, and then the height was 90. This is the potential energy. It was at point A was 90. Okay, and you should get about 42. You would get 42.4, I think, if you use 10 instead of 90. Perfect. Calculate the speed of the car at point B. Okay. Let's take a look. So where is point B? Point B is here. Okay? Point B is right here. At this point, at point B, we're going to be moving, so we have kinetic energy, but we also have some height now, so we also have gravitational potential energy. It's supposed to be a U sub G, okay? So in the beginning, we have only gravitational potential energy. At the bottom here, at point P, right, we only have kinetic energy. But at point B, we have a mix of both kinetic and potential energy. Okay. Let's take a look. We're going to solve this very similar to how we solved the last problem. We're going to say the initial energy equals the final energy, because there is no work being done, because Earth is part of our system. If Earth was not part of our system, there would be an external force which would cause work to be done. And the work being done would equal the change in energy. Okay? But we are saying there's not going to be a change in energy. There's going to be a change in the type of energy, but there's not a change in the total energy. So the initial amount of energy should equal the final amount of energy. Initially, we said there was only gravitational potential energy. Okay? This was at point A. In the end, we have both kinetic energy and gravitational potential energy at point B, because it's got some height and it's moving. At point A, it wasn't moving, so there was no kinetic energy. Okay. Let's break these down into equations. This is mg times the height of A. They didn't give us a variable for that, so I'll just put h sub A, the height of A. And then for kinetic energy, this is 1/2 mv squared plus mgh, and this is at height B. Okay. We are going to solve for velocity, so this is what we need to rearrange for, velocity right here. We can cancel out m's because everything has m. Can we cancel out g? I see g on both sides of the equation. I cannot do that because remember, for me to cancel something out, every single term has to have that variable. This has g, this has g, but there's no g here. So I cannot cancel out the g. I cannot cancel out the h's because one thing, they're different h's. This is h sub a and this is h sub b. But I can't cancel the mass because everything has mass. Okay? Let's rearrange for v. So this is g h sub a minus g h sub b equals 1/2 v squared. I'm going to clean this up a little bit by taking out the g, h sub a minus h sub b. And this is 2 square rooted equals v. Okay. That means that this is the square root of 2 times 9.8, or you can use 10, times the height of A was 90, and the height of B was 50. Let me just check to make sure that's right. Yeah, height of A is 90, height of B is 50. Nope, where am I? And this came out to about 28. And this is a velocity, so it's meters per second. I forgot to put that on the other one. Don't forget your units. Perfect, so that's how fast the car is moving at point B. On the figure of the car below, draw the and label vectors to represent the forces acting on the car when it is upside down at point B. Okay? Now, this car, when it's going around this loop, is undergoing circular motion. And we know that for circular motion, there needs to be a centripetal force to get centripetal acceleration. Right? That's what causes things to go in a circle, is centripetal force. So I know that when I draw these forces, there needs to be a net centripetal force pointing towards the center of the circle. Here's the circle. Right? This car is going through the loop. Okay? So we have a downward force of gravity, right? Force. And we also have a downward force normal. Okay, this is the track pushing down on the cart. And notice these, we have a net centripetal force pointing towards the center of the circle, which causes our centripetal acceleration. Okay, calculate the magnitude of all the forces identified in this first part. So we need to find out the force of gravity and the force normal. Okay, force of gravity is equal Easy. The force of gravity equals mg. Right? Now the cart was a 700 kilogram cart. So this is 700 times 10. Or you can use 9.8. So this force of gravity is 7,000 newtons. Okay? It comes out to 6,860 if you use 9.8. Right? How do we figure out force normal? Okay? We would need Newton's second law, and we're going to use Newton's second law for centripetal motion, or circular motion. So that says that the sum of the centripetal forces equals mass times the centripetal acceleration. What are the centripetal forces? Well, we have force of gravity, and it's going to be positive because it points towards the center of the circle. And we also have a positive force normal, and it's positive because it points towards the center of the circle. We have mass, and then remember we can break centripetal acceleration down into v squared over r. That's squared. V squared. Perfect. We are solving for force normal. We are solving for this. Okay? So that means if I move, this is, or let's just do this. This is mg plus force normal equals mv squared over r. That means that the normal force is equal to mv squared over r minus mg. Okay. That means, let me bring this up here. Okay, now we're ready to plug in numbers. The mass was 700 kilograms, right? The velocity, we found the velocity earlier, it was 28 meters per second. That's how fast it was going in the loop. So 28, and then this is squared. Multiplying those two. And we're going to divide it by the radius. The radius I believe was 20. Yeah, the radius here is 20 meters. All of this minus, we already said the force of gravity was 7,000. So minus 7,000. When you plug this in the calculator, you get about 20,580 newtons. Okay. So in this case, the normal force is actually a lot greater than the force of gravity. Perfect. And that's it for that problem. Hope everyone's doing well. Remember, May 14th at 1 p.m. you have your AP Physics exam. Guys, this is, make sure you have all of these answers that you're doing for all these free response in one spot, maybe a nice notebook. And make sure you're putting in notes in there. When you're doing the problem, make sure you write down the problem, draw the pictures, so that you can use this on the exam. Remember, it's an open note exam, and I feel like these problems, you know, you'll come up with a problem and you'll be like, hey, we did a problem very similar to that one. Let me look at that one. Again, it's open notes, so there's nothing wrong with looking at your notes. And writing stuff down. So just keep at it. I know you guys have a lot on your plate with all your AP classes right now, but just keep doing practice and you guys will be alright, okay? Alright, peace.